So what was the period or the frequency?
A second.
Yes, it was. So we have 440 hertz, and we played a 439 on top of that. And here's the sophisticated math, if you're ready for it. The beat frequency, subtract. It's the beat frequency. And since the period is the inverse of that, or the reciprocal of that, the period would be, the beat period would be 1 over the beat frequency, which would make it 1 second. So if I played 440 and 439 and a half, what would be the period?
Half a second.
Say it again.
Half a second.
I know how you got that. You missed a step.
Two seconds.
2 seconds. The difference in frequency is a half a hertz, the reciprocal of 2. Let's find out if I've been lying to you or not.
What's the formula again? Just subtracting the two?
Yes. It's as difficult as that. All right,
Well, then dividing by whatever you got when you subtracted, right?
say it again.
Then you divide whatever you got as the denominator of your one, right?
Yes,
Okay.
they get the actual period, beat period. All right, so here's 439 and a half, 440. If I've done it right, they should both already be playing. So, beat frequencies. Now there is something I skipped over, but we'll probably either pick that up next week or you'll pick it up on your own. Questions up to here? There was one time I was playing around with this right before class and put it on some high frequency and then forgot. I forgot to stop it, but I couldn't hear it because of my bad hearing. And a couple minutes into class, somebody said, "Does anyone else hear that high-pitched noise?" Oops. All right, so since we can make sounds go differently, there was a question in the conceptual physics book about would you hear it if, it's 20,000 hertz is above most people's hearing, if not everyone's. So if I played at 20,000 and 20,500 hertz, it would have a beat frequency of 500 hertz. And the question is, could you actually hear that? Well, according to Hewitt, who wrote the conceptual physics books, you can, but it's very difficult to find anything that will play those frequencies. So if you happen to have software that will play above 20,000 hertz, I'd be curious to see if you actually can hear those frequencies.
I remember reading somewhere that if you played a piano key 440 hertz, it would just sound like a sine, or 440. I guess that's not really related.
I would hope it would sound, I mean, I forget which
I
key
mean,
it
you
is.
don't hear the notes anymore. You just hear the 440 hertz.
Ah. All right, so I have some source here. I'm gonna label it E for emitter. That's gonna give out a sound wave. So you get this pulse, and then you get another one, and then, so basically through some period, label it T sub E, the period from the emitter's point of view, we get this wave going out. So imagine you got a very still pond, throw a rock into it, boom, and you get that wave. And then you throw another rock in the exact same spot, you get a second wave, and every second or every 2 seconds, some periodic time, you keep throwing a rock into the exact same spot because you are that good, and you get this ripple of waves out. If instead of I send a rock a hit there, I get this wave, so it's sort of in a frame set. So that first wave is out like that. So the second one, you throw the rock, not there. Wrong one. There we go. A little bit ahead of it. So we have this first wave that is centered at that spot. The second wave is centered at this spot. And then you throw a rock the third time as you're moving to the right. Notice that you get these waves that are closer together here than here. When you're doing the overhead view, this represents the peaks, and halfway in between would be the troughs. So if I have a wave like this, I would represent it from this point of view, the overhead point of view, as peak, and then a trough in the middle. If you're a bug on the water here, sure, it's a bug, you're going to be hit by waves much more frequently than if you're over here. So this is a higher frequency than that is. If this were a sound wave, you would be hearing a higher frequency. Now, some books go the distinction between pitch and frequency. I don't, I just use them interchangeably because I was raised by wolves. However, I guess you hear a pitch because of the frequency, but I will still use them interchangeably. At the same time, in this case right here, if I have something still, and these waves are going out, if I have a receiver, little r, heading towards me, it's going to be hitting these waves more frequently than they're being emitted. So again, you're going to get a higher frequency if it's coming towards you, going towards the source. Not aware of where we're heading, this is the Doppler shift. Up on the floor, of course. So what we're going to do is derive this Doppler shift. So I have a wave that is sent out in that direction. Sent out in all directions, but I only care about that direction. So I have a wave that's sent out, so at some time, I'll have a wave there, I'll have a wave here. Actually, let's do it this way. So I have some source, some emitter that's traveling in this direction at some speed v sub e, and I have a receiver heading towards me at the same time. So it sends out that first wave. So I got that first wave that starts moving this direction at the speed of sound, v sub s. At the same time, I've got my emitter also traveling in that direction. So after one period, it's going to send out a second wave. So it's traveled v sub e times t sub e. That's how far the source has traveled, the emitter has traveled, and the wave has traveled this distance here. So v sub s t sub e. So from the source's point of view, that's the wavelength, distance from peak to peak. So the wavelength from the emitter's point of view is VSTE minus VETE. At the same time, the receiver's coming in. So I've got this wave right here, so let's give myself some room over here. So he's traveling, he hits that point at what he considers time is 0. And then he's going to, at the same time, this one is emitted, so this is my wavelength from the emitter's point of view. But once he crosses that threshold, this is still going towards him, so he's going to hit it here. This would be the wavelength from the receiver's point of view. The distance that he has traveled, this part right here, is the speed of the receiver times the period of the receiver. And this distance right here is how far the wave has traveled from the moment that the receiver crosses that threshold. And so this is going to be the speed of sound times the period of the receiver. So what we get is that the wavelength from the emitter's point of view is going to be equal to VSTR plus VRTR. Well, those are equal to each other. I want to get the, so I get VS minus VE times the period from the emitter's point of view is equal to VS plus VR times the period from the receiver's point of view. Since I'm concerned about this one right here, I get TR is equal to VS minus VE divided by VS plus VR times the period from the emitter's point of view. Now typically, we don't notice the period. Car's coming toward you, you're not going, wow, that sounds like about half a second per, no. We hear the frequency or pitch for purists. Well, what's the frequency in relationship to the period?
1 over.
So 1 over the frequency from the receiver is equal to basically the reciprocal of that. So the frequency of the receiver is equal to the frequency of the emitter times VS plus VR over VS minus VE. If you're heading towards each other, you're going to get a higher frequency. That's basically doubled up here. If I make the denominator smaller, I get a higher number. If I make the numerator bigger, I get a higher number. So if they are going towards each other, because that was what I started with there, if they're going towards each other, this is the way you would set up the equation. If they're going away from each other, well, you should expect a lower frequency, so VS minus VR, and VS plus VE. Now, I've seen books go into set up a table in the 4 different situations, but in essence, what we're dealing with here, the frequency of the receiver or observer is equal to what's emitted times VS minus plus VR over VS plus minus VE. This is the typical way that you're going to see it, and you just think through it. If the emitter is heading towards the receiver, you want to make the fraction bigger, so you'll subtract. If the receiver is going away from the emitter, then you would expect a lower frequency, and so you would subtract there. So if they're chasing each other, you expect them to, you'd subtract both of them. If they're going the same speed, or same velocity really, if they're going the same velocity, then they'll both be minus, and you'll end up with what's emitted is what's received. Because from their point of view, neither of them is moving. That is the Doppler shift. Now suppose VR is 0. So you got a receiver just sitting right there. You got an emitter traveling this way at the speed of sound. What happens? Oh, there should be V. Yeah, V equals VS.
the receiver would never hear it.
Why?
Because even though the sound waves are moving rearward in this situation, at 700 miles or whatever it is, they're also already moving, they're being emitted from something that's moving at that same speed.
Okay. Mathematically, what would happen?
What's the situation again?
Receiver sitting still and the emitter is heading towards them at the speed of sound.
Oh.
What happens mathematically?
Would the denominator go to 0?
Yes. So what the receiver would have would be infinitely high frequency, which would not hear. But let's think about, so this sort of breaks down at that point. And if we exceed the speed of sound, then, well, then we start getting in negative frequencies, whatever that means. So this is valid as long as we're going under the speed of sound. But if we're going the speed of sound, we let out a wave here, and then I let out another wave right on that spot, and so basically I double it up. And then the next time I come around to make the sound wave, I triple it up, then quadruple, and remember, the peaks of these sound waves is a bunch of air molecules really compressed together. And it builds compression upon compression upon compression. Assuming that the emitter is not falling apart at this point, and a lot of planes did, especially early on. But what you're doing is you have this huge spike in the sound wave and you have the sonic boom. It's one compression wave on top of the other. A lot of constructive interference. And a lot of vibrations to the plane or whatever you happen to be in. But that is where we will end it today. Wednesday, you're going to be playing around with this. And fun will be had by all. Of course.